Wait, let's start. It's my pleasure to introduce Mitra Baratchi. She's associate professor at LIACS, that's the Leiden Institute for Advanced Computer Science. She's very well known for her applications of AutoML in domains such as spatial-temporal learning, time series, mobility. She works with the European Space Agency, companies like Honda and so on, so lots of interesting projects. And while we use AutoML to model tables or recognize cats and dogs, she actually built a model of the entire planet Earth to help with climate change. So that's very impressive. And she also put out a survey lately about AutoML for the younger people here. Definitely check that out. And with that, let me give the floor to Mitra.
Yeah, great. Thank you very much for the kind introduction. I'm very excited to be here to talk about some of the works we are doing to take AutoML, be able to work with raw spatial temporal observations and help people to make decisions so that they can address some of the nasty problems of the world. Yeah, before everything, I would like to give an acknowledgement to all my collaborators. What I'm going to talk about is collaboration with a large group. First, a shout out to the graduate students, masters, and PhD students who are doing this research, and other collaborators within the AutoML community, and also other scientists, atmospheric scientists, Earth observation scientists, Earth scientists. Yeah, so with that, let's get into it. So imagine that I hope we all have this visionary goal that we want to have AI that can help decision makers address important challenges like, for instance, global warming. And that means that we need to have AI that help really to make decisions, not just to predict what's going to happen, but being able to predict what happens if we enforce a certain policy. So what has to be stopped and what can go on, decisions like this. So we want AI that help us to make decisions, better decisions. And if you think about the Earth itself is composed of 4 different subsystems, complex subsystems. And luckily, nowadays, we have data sources generated by satellites, sensors, IoT sensors, our mobile phones that are making spatio-temporal observations of what's going on the Earth. And if we want to address problems in the world, we have to create knowledge, meaning that we should be able to create models of the system of systems, the Earth, representing the interaction between different variables in these systems. And this is, I'm happy that this was brought up. It's really about causal interactions between variables within a system and also within subsystems. So this is kind of an aspirational goal. How can we create knowledge using existing data to know what's going on in the Earth? So then when we have this kind of knowledge, we can also assess the impact of intervention. So what's going to happen if we change, for instance, the traffic on the roads? And it's interesting to know when I talk about like spatio-temporal data sources, for instance, Earth observation, there's quite a lot of data that is open. It's collected by taxpayers' money, so everybody can use it. So anybody's free to use it and work on machine learning problems. But yeah, so my research is mainly about working with raw data, so raw data that is available and free for us to use. And but that's not easy because raw data comes with, for instance, a lot of missing data. When, for instance, when we talk about Earth observations, you have a lot of clouds. You have data with different resolutions from different sources, and there's also a lot of noise. So, for instance, if you have what on the right, you see is on the top is an actual trajectory. On the bottom is what a sensor would measure, a GPS sensor. So there's a lot of noise. And when we are building models to work on raw data, they have to be robust. So they have to work on this form of data. And yeah, so to move towards this vision of being able to create a model of the system of systems, we need automated solutions. First, that they should allow us to perform tasks on this single data source with all these imperfections, with the noise, missing data. Then to be able to create knowledge using all the data sources that we have, not only satellites, but also satellites, mobile phones, and sensors on the road. And at the end of the day, let's not forget that data is not all the knowledge that we can get. There's already a lot of knowledge, and there is so much we can get from data. So we should be able to complete and get a full picture using the domain knowledge. Yeah, so this is what we need, and we need automated solutions for all of these. And we hope that automated machine learning can help us do that. So this is the automated machine learning perspective. So let's define a search space, all the design choices for a specific problem. Let's define a search strategy to search within the search space efficiently and assess models based on certain performance criteria. And based on this, we already have a lot of great AutoML systems built by this community that can perform machine learning on tabular data sets or in general neural architecture search. But if we want to address like problems that I mentioned, we have to reflect a little bit on what needs to be in this system. So in terms of design choices or search, what's in the search space, there are other algorithms that need to be considered. So there are algorithmic design choices. There are data-related design choices. And then if you also want to somehow embed domain knowledge within this like whole pipeline of creating a machine learning model, there are design choices related to that. And then also in terms of model selections, for a lot of problems, we cannot use cross-validation anymore when we're dealing with unsupervised learning problems. We need to think about new objective functions that are relevant for, like if you think about this whole vision, and then also sometimes more objective functions. And once we have some more knowledge of the problem, then we can also improve, like by studying the loss landscape of the, during optimization, we can also improve these models further. So I want to give some examples, and the key thing about all these examples are they're either from time series, like machine learning for time series data, or other spatio-temporal data sources. So I want to start with this, one of our early works on automated machine learning for early time series classification. So early time series classification means that in a lot of applications, if, for instance, the classification of a label of a time series would take a long time, for instance, 24 hours before we define the label, we want to do this as early as possible. So this is the idea of early time series classification. In this case, we have two objectives, so earliness and accuracy. And typically when you're trying to be very early, the accuracy drops. So there is a clear trade-off between these two objectives. There are already a lot of machine learning algorithms designed for this specific problem, but all of these algorithms have only one hyperparameter that controls earliness and accuracy, and the suggestion is just tune this hyperparameter and decide what kind of trade-off you're interested in. So we wanted to address this using automated machine learning, creating a search space of existing early time series classification algorithms and their hyperparameters. So suggest configurations. And in this case, this is a multi-objective optimization problem. We needed to have a configurator that would be able to assess performance of the model configuration based on multiple objectives. So in this case, we use ML-Param ILS to address the multi-objective cache problem. And just a background, so what such configurators would produce is not just a single configuration, but a number of configurations that we show on a Pareto front. And how we assess the quality of such configurations is that the more you have, the better, because then you would have, a user would have more options to select to achieve a certain trade-off. And then this hyper volume, and then you can imagine if you're more towards, so if you assess the performance in terms of earliness and error rate or accuracy, the more towards this other corner, the better. So that's hypervolume, the bigger, the better. This is how we assess. And what this means for the existing algorithms, what I'm showing here is a number of algorithms in the search space. If you just look at what's possible when you optimize only one hyperparameter that is suggested, you actually don't have a lot of trade-offs. So the user doesn't have much options to select, although they're already tuning a dedicated hyperparameters to achieve this trade-off. And when we combine all these algorithms and consider them in a search space, there's already a Pareto front that there's more solutions there. And so I have the hypervolume also on the top. And when we also optimize other hyperparameters of these algorithms, then you would have more solutions and higher hypervolume. And what we did here, we actually added a very simple naive algorithm to this search space that doesn't do something really smart. It's just always classifying a specific prefix. And even this algorithm, when you consider it in the search space, also adds more to potential solutions. So this shows that when we address problems like this, there's more options. There's to benefit from all the algorithms that are possible. And hopefully there are more for the users to select from. And here we have the ranking results on 115 data sets. Well, again, so when you optimize all these algorithms separately and in a single objective case, so we call this system AutoML approach multi-TSC. So it's ranking quite well. And what we did, we tried to improve this a bit further. So here I have 3 versions of this multi-ETSC. So the one, I hope that I can get them up. So this is when we don't have this new algorithm in the search space. In both other cases, this algorithm is in the search space, so it's already improving. So we see that this naive algorithm, when it's in the search space, it's improving the results. This is the version where we are optimizing on all the hyperparameters and algorithms at the same time. And this is a version where we have one important knowledge here, that all these algorithms have one hyperparameter that controls earliness and accuracy. And using this knowledge, we just prioritize on when we are optimizing to optimize that hyperparameter, and that also helps. So when we have some more knowledge, I mean, we can still improve. So this previous algorithm was already like using algorithms that are there. So this second example is related to a problem that's, well, we don't have a lot of algorithms for it. So we tried to approach the remaining useful life estimation problem using automated machine learning. So this is done in collaboration with KLM. So KLM has a lot of engines and a lot of sensors on them. They're interested in knowing where would these engines break. So just predicting the remaining useful life of these engines. So in statistics, this is related to survival analysis. But here the problem is that we have multivariate sensors of different kind. So it's really a complex time series problem. And yeah, so it's common to use deep learning for like in literature, so not traditional statistical approaches. So this is the idea of the idea of remaining useful life estimation. So you have a lot of data over time. And well, you know, this is like kind of the status of health of a machinery. It's when you start, everything is going fine. At some point, some degradation starts happening. And then at some point, the machine breaks. So the idea is just to predict this point at any point in time, so that you can, well, know where you have to do repair. And so if you want to treat this as a regression problem, the problem is that at any point in time, you have some window of observations, multiple time series, and then you want to predict where on this curve you are. And then from this prediction, predict where would this point happen. So this is kind of a 2-level thing. But what you have to think that this curve is an imaginary curve. This is what we imagine. when we get data for training, typically we have a bunch of sensors that were running for a period of time and the point where this machine broke. So this is the only data we have. So if we want to turn this into a regression problem, we have to also imagine this curve so that we can train a regression model. So we wanted to address this through neural architecture search because I mentioned there's a lot of new models. They're using neural networks for this kind of problem on multivariate time series data. And so the requirements that we should be able to also create this, what I call the target remaining useful life curve. That's kind of our labels automatically also. And at the same time, users of this kind of models, they're not just interested in knowing where would a machine break. At any point in time, they're interested in knowing how confident the model is that the machine would break at that point in time. So for them, uncertainty is more important than just predicting when the things would happen, because they can continue observing and just doing predictions until they are confident that the predictions are stable. So we created a search space that had two sets of hyperparameters. The first set is pre-processing hyperparameters to create this imaginary RUL curve. In this case, we simplified it. So the curve is at some point the device at the early stage is doing fine, and then degradation starts. So we have hyperparameters to control the shape of this curve. First, where do we start? Where is this point that we call a reflection point when degradation happens? What is the degradation style? Is it linear or is it nonlinear? And then also the window size, because we are dealing with a time series problem, we have to look at data over some period of time. And the rest of hyperparameters are normal hyperparameters when you design neural networks. And for uncertainty estimation, we have we'll consider two types of uncertainties. One uncertainty is the uncertainty of the model coming from the parameters. This is what we want to minimize. We want to have a model that's a bit more certain. And for this kind of problem, the user would like to also see a probability at any point in time that the device would break at that point in time. So they want to see a probability, and this uncertainty in survival analysis, typically outcome is modeled as a Weibull distribution. So this is a common probability distribution for this type of problem. And we predict that the parameters of a Weibull distribution. This is how we generate neural networks. And again, we treat this as a bi-objective optimization problem. So we want to have a model that has less uncertainties and low error. What we have here, the blue points are configurations on the validation set, and the red are configurations on the test set. So at some point you see that, well, there is quite some overlap and some places not. So this is still work in progress. So how can we generalize better? And in the hindsight also, this is for me an open question. Is it true that a model with low uncertainty is always better, or is it more important that the model is more stable in terms of the uncertainty? So a stable model, even uncertain, is better than a model that's uncertain. It's just like humans. Sometimes people are very certain, but doesn't mean that they're always correct. So as long as we can model and evaluate what is the quality of uncertainty estimation, that's, I think, better approach. So this is what we're at the moment working on. The other problem I want to talk about is about data fusion for Earth observation. So this is related to the collaboration we had with European Space Agency and the Dutch Space Research Institute. ESRON is the Dutch Space Research Institute. So their problem is there are atmospheric sciences, and in ESRON there is a satellite developed for detecting methane or atmospheric gases, and specifically methane is very important because, you know, methane is the most important gas responsible for global warming. So it's very important to detect what they call methane plume. Where is methane happening? And this is, in general, a more general problem when in Earth observation. In a lot of applications, the interest is just detecting one thing against everything else. So it's a binary classification when we're interested in detecting something that's very rare against everything else. And then you can start, I mean, this is kind of how things start. So you detect, or what is the most, or you imagine what is the most relevant data source for this. In this case, we want to detect methane plumes. So we have a data layer methane concentration. So we start with that, collect a data set, train a binary classifier. And then when we apply it, then you realize there's a lot of false positives because, for instance, what is shown here is that something that looks like a methane plume is actually not a methane plume, it's an albedo artifact that looks very much like a methane plume. And then in order to address this problem, then we think, okay, so for this artifact that we detected, what is the most relevant data layer to consider that? And then you add another data layer, but then you realize that there's another artifact because false positives are a lot. So what we wanted to know is that if we can just make it easier for users to fuse all the data sources that they have, so to hopefully to speed up also this process. So we thought to create a neural architecture search system for data fusion, multimodal data fusion. So in Earth observation, the problem is very different than when we were dealing with data fusion images, because typically in image processing, the idea is that you have two images, for instance, over a different period of time of the same area, and then you want to detect an object, but this is really multimodal. You have different types of data. So hopefully this would allow, automatic feature extraction if you address it through neural architecture search and allow model complex relationships to improve the prediction accuracy. And I have to say, like, for instance, in this case, in our collaboration, we see people use quite a lot of manually designed features. So we want to speed this up. So we designed AutoMergeNet by creating a search space inspired by image data fusion literature, all the backbones that are used for data fusion. And then we identify extra hyperparameters, the fusion depth, typically either early or late. This is the approach, but we try to treat that as a hyperparameter, and also the fusion strategy. And we used BOHP as a search strategy. And then this is just sample results on a methane data set against some baseline. So the last line is AutoMergeNet performance. It's quite well in terms of accuracy, precision, and recall compared to other baselines. So these baselines are also optimized in terms of hyperparameters, but they're a single network. So we consider all these types of network backbones in the AutoMergeNet. But so this is quite encouraging. But for our collaborators who are actually interested more in the application, what happens if we use these models in practice? They already have a model that's implemented in operation with heavy feature engineering, and they want to know should we replace that model with this model? And for this, they created they gathered a new unseen data set by both of these models, and then just fed these. So this is 17,760 images. They fed it to both of these models to see, and then they look at the detections and then try to label them to see what is the performance. And this is the result. So the one on red is the model in operation, detects 57 plumes that our model doesn't detect. Our model detects 43 that their model doesn't detect, and there's only 30 common detections between the two methods. So I think this just says that when you go towards real life applications, problems are much more challenging than what we think. So just numbers, high accuracy numbers doesn't say that the model would work in practice. And this is still work in progress, so we're looking into this. But I think what my hypothesis is that we need to have models that are robust to work on real data, because we don't know what happens on real data. If you have a little bit of noise in multiple data layer, any of them, how would that have been detected when we run the models in operation? And the next work I want to talk about, it's a little bit different. So it's about, well, how we can use still this idea of automated machine learning while developing new algorithms to automate furthermore. And with this, I want to talk about an algorithm that we designed for spatial interpolation. So in a lot of cases, what we hope to get as a data layer is something like this, but this is what we get in practice. And so with a lot of data sources, there's a lot of missing data. And so if we want to still use this data, we need to be able to fill the gaps. There are different approaches for this. Typically, we address the problem as a regression problem, for instance, using neighboring cells to regress the value of missing point, or considering the distance of other points and then weigh based on the distance, what is the impact of other points to regress this value. What we thought, it's important to have a system level value through propagating the value of all the cells when you want to regress a specific cells, all the cells throughout the network. And this is inspired by Markov reward processes. And so this is one thing we want to do. And the other thing, it's very common that we have one data layer where we have some missing values, but then we have another data layer where we do not have missing values. So how can we use this information of the spatial autocorrelation between cells and transfer that knowledge to fill these missing values? So we want to take other data layers as features to help us improve how we can fill these missing values. So we came up with an approach based on value propagation that does two things. One is that looking at another data layer and derive the weight between, well, every cell, every pair of cells, neighboring cells, as an impact that they can have on each other. And then the other thing is that, inspired by Markov reward processes, what we imagine that the value of each cell, so each cell is a state and neighboring cells are other states that we can transition to. So the value at each state is the sum of reward of being in that state plus the weight that comes from these other data layers multiplied by the expected reward of transition to the other cell. And then we came up with an approach, a light approach, to iteratively propagate the values within a grid cell, which is very light. In few iterations, you just propagate all these values considering these weights from data layers. And here's some results and how this works. So it just brought some visual results. I think it's more detectable than quantitative results what happens. So this is our approach. This is how it performs. This is kriging, which is a common approach for this problem. And then we have spatial autoregressive approach where you regress from neighboring cells, and a CNN approach. Both these approaches we implemented through automated machine learning, meaning that we selected the best regressor and then optimized their hyperparameters. In this case, for spatial autoregressive interpolation, we use autoscalar. So there's also some ensembling going on. For CNN, we use autokeras. So it's like the best we could do with existing algorithms. And so our collaborators in European Space Agency, when we presented this idea, they said it's actually it's interesting to see if this is going to address our problems with having clouds in a lot of images. So would you be able to, interpolate what's going on under the cloud? And we thought, okay, so we can, so now that like the real problem becomes more challenging, because then you have cluster, like missing data are clustered, they're not random anymore. And we thought, okay, as a feature image, we just use another image of the same place, sometime where there was no cloud. And then this is the target in this case. So you see there is quite a lot of difference. So over time, things change. And we found some additional challenges. So one of the challenges is temporal heterogeneity, where we have a scene like this, where you have vegetation that are quite dynamic next to a road, which is very static, and then a sea, which is dynamic in a different way. And so we call this temporal heterogeneity. And another problem is a scenario like this, where you have like a glint, which is, imagine that you want to propagate this value, and then the whole method would break. And this could also happen if you have noise. Just a single noisy pixel makes the method break. So we came up with solutions for this. Just in short, these are, so for temporal heterogeneity, an approach to prioritize within objects relations when we propagate the values. And the other one is to enforce some kind of resistance when you go towards extreme values. And both these approaches just introduce more hyperparameters. Now, one of the strong points of this algorithm is that it's training free. The only thing you need is an image with some missing values and another image of the same area without any missing values. You don't need to do any training, and also during inference, it's very light. So it has its own advantages. But now we have extra hyperparameter that have to be tuned per image. And so Earth observation have more bands than natural images. So we have 12 bands. And then we wanted to just test how this works on 400 patches. These hyperparameters have to be tuned for all of these. So we came up with auto adaptation by treating these as hyperparameters and taking cells where you have actual values as validation set and try to tune these hyperparameters per image. So it's fully automated now. And here, just some qualitative results, how it's working. So I'm comparing in this visualization the error that we get from vPint and this AutoML approach for spatial autoregressive interpolation. So where you have red in these images, by the way, these are different types of landscapes. We want to know if it's actually always working. Where you have a patch of red, that means vPint is performing better. Where you have blue, that means the AutoML approach is performing better. And when you have somewhere in between, it's just the errors are both of methods comparable. So for instance, in this case, you see that vPint is performing much better, here AutoML better. And this just, I think, just confirms that we need new algorithms. And then ideally, if we can create better ensembles, we should be able to benefit from all these algorithms in one system. But also interesting to know if we can predict where each algorithm would perform. Okay, the other problem that I want to talk about, this is actually something that I'm really passionate about, because it took some time to come to the place that we are, and through collaborations with people in environmental sciences and also people in astronomy. And this is about automating inference using physical models. So the reason why I say it's interesting for me is that this area is completely new. I didn't know anything about physical models and their importance and what role they can play in making use of spatio-temporal data. And so these are some of my observations through collaborations over time, that a lot of interesting problems in sciences are regression problems. So we have some kind of observations, we have Earth observations, we have data from telescopes, but what scientists are interested in are regressing a very detailed parameter, not just classification. They really want to know about the parameters, but their approach to regression is very different from the approach that we take. in regression. So I want to continue with just an application in ecology. This is something that we've been working for some time. Where you have Earth observations, so these are real observations we get from satellites. And also ecologists are interested in detailed biophysical parameters, LAI, chlorophyll content, water content of vegetation on the Earth. A machine learning approach would be just create a labeled data set and do a regression, train a regression model. But this approach is not taken. There is at all. And we tried to do this and we also failed because one thing is that the resolution of satellite images, pixels, is much bigger than what, if you think about the chlorophyll content of a leaf. So there is not really proper, the scales are quite different. And then there's also a lot of spatial heterogeneity in space, and also over time things change. Even if you use, there are actually data collection campaigns, and all ecologists put they share all their data in somewhere. So there is already a lot of labels that were acquired through lab and field work. So they pick a leaf, they put it on a scale, they measure it, and then let it dry, and then measure it again. There's a lot of this kind of work. There is some labels available in some repositories. Everybody shares their labels over time. But the problem is more difficult. This is not really a machine learning problem. So the way, the common approach in the domain is that they have physical models for this kind of inference problems. So these physical models receive these parameters that we are interested in inferring, and there is a simulation model, and they simulate something that looks like Earth observation. And you can do different things. You can simulate a lot of data and then train a machine learning model to do this. So we call this inverted inversion of a physical model is more interesting because we want to feed observations and get the parameters. So you can use machine learning for this. This is one common approach. And the other thing is using optimization. And I mentioned that we have to use the domain knowledge. This is what I like to mention, that this is an example of domain knowledge that we need when we want to infer from existing data. And this is interesting because it's a registered domain knowledge. So we can work with it. It's a physical model, it's registered. We can work, computer science can also work with it. It's not just in someone's brain. It's already available for us to use. So if we want to treat this as an optimization problem, so we have parameters, biophysical parameters that we feed to a physical model. We have simulated observations. We look at the difference between these simulated observations and real observations, and then try to select biophysical parameters that help us minimize the loss. And so this is the approach, but there are two fundamental problems with this. One problem is what they refer in the field to as an ill-posedness of this problem, meaning that you might have very different combination of biophysical parameters that lead into the same simulated observation. So this inversion is actually ill-posed. It's impossible to go back to only one solution. And then, by the way, so these parameters that I'm showing here are typically a vector of parameters. So there are 10 different parameters, LAI, chlorophyll content, water content, everything related to biophysical parameters, biophysical property. So the manual solution that's used to address this problem is that either the number of free parameters are limited. So we limit the number of free parameters and only try to estimate one parameter, or users typically constrain the range of parameters using their own knowledge, like looking at the landscape. It seems that LAI in this range makes sense, but this is, I don't want to call it ad hoc, but this this method doesn't scale very well. So you cannot use now all the data you have to infer what happened on the Earth, like since 50 years ago. So this is really, yeah, it's not scalable. But if we want to create more knowledge, we want to have automated solutions to help inferring from existing observations. Another problem is the problem of noise. So here we are presenting the loss landscape using a simulated data. And imagine that we have a global optimum. Here, this is the star. If we added, so in this case, we added a little bit of noise, and the noise is present in the real data. It's not present in the simulated data, but it's present in the real data. So this global optimum position also changes. So we also have the problem of noise, and we also don't know, well, we know there is some noise in real data, but we don't know how much noise is that, how to model the noise. So there are like these problems. And then we thought, okay, so this problem is a challenging problem. Inference is not possible, but how if we can, just looking at this loss landscape, identify the range of possible solutions. So at least a user can better decide how to set priors, and then not to have free parameters. So just look at what is possible, and then we think this is more closer to uncertainty estimation. So estimate what is the range of possible solutions. And then it's an optimization problem, but interesting thing is that, so at least here we have looked at the landscape of one of these models that's very common in ecology. Almost every ecologist uses it. So we thought first maybe we would have like multiple pockets of different, possible solutions. In this case, we found that actually there's only one pocket, but this pocket is kind of like a bathtub. So there's a lot of solutions on the bottom of the bathtub. There's not only a single global optimum. There's a lot of solutions kind of equal there. So we want to identify this area. So the approach, we have an algorithm that looks for this optimum and then starts sampling around it. But then we want this to be scalable for other types of physical models. So we are making sure that's also working in a multimodal case where you have multiple of these kind of surfaces. And here's how the results look like. So we think this is closer to uncertainty estimation. And we thought as a baseline, you can take any kind of machine learning algorithm that allows us to estimate uncertainty, for instance, random forest, and compare the results. So here random forest is trained on simulated data, and we have using grid search. And by the way, I have to say, we're here just for visualization, we're looking at 2 parameters. There are 15 parameters in this type of model. So we look at using grid search, we have found the area of potential solutions, and our algorithm is able to detect this area. And this is what random forest produces, this diamond, because it's actually not made for this problem. And we don't have algorithms for this problem. And this is where you have, we have noisy simulated observations also working well. And this is where we go to real observations. So real observations have some noise that we are not sure about, and things become more challenging. So so the ground truth area is broader than what we can detect. So this is still what we are working on, but we hope that we can, address more problems with different physical models in different domains and just scale this work up. And so here a few takeaway messages from this talk. And how can automated machine learning help us to make better use of spatio-temporal observations towards making decisions? One is that we have already a lot of algorithms, and treating problems that automated machine learning help us to make better use of existing algorithms, improve them, by having more objectives, but also improve the quality of the solutions that we have. There is still room for new algorithms, and algorithms are complementary. This is, I think, I'm not the first one to say, it's already confirmed by the community. And then I hope that we can well, it's very important to understand that not everything we want to do with data is machine learning. So it's we still have a lot of data, and if we want to do inference using this data, machine learning is not the answer to all problems. So we hope that we can address problems beyond machine learning. And I was excited that this topic of causality was brought up. So I'm here with a paper. We have a workshop paper on automated machine learning for causal discovery. So I hope to talk to you later about this work. And just along the lines, the same lines, we have a postdoc position for 4 years to continue on what we are doing on causal machine learning, hopefully, better causal machine learning using automated machine learning from spatio-temporal data sets. So if you know anyone or you're interested, so there's the application deadline is 30th of September. And by this, I'll go back to this slide. And thank you very much. I hope to be able to answer your questions.